Keeping your robot's gripper perfectly level while it lifts is a common engineering challenge. And a virtual 4-bar lift offers a really smart solution. But lots of people see these mechanisms, don't quite get the mechanics, or when to pick one over a simpler 2-bar or traditional 4-bar. In this video, I'm going to show you how a virtual 4-bar lift works. You'll understand exactly how they operate, especially the pulley or chain systems that make them virtual, and why this design can give your robot stability and control of whatever you're trying to manipulate. I'm Brogan Pratt, and with over a decade in robotics education, I've seen firsthand how mastering these kinds of mechanisms can give you more tools in your toolbox when you're designing robots. We'll start by looking at the basic principles of a few common types of bar lifts, and then I'll show you how a simple pulley system creates that virtual 4-bar magic. So at the workbench here, this is the robot we're going to be using today to take a look at some of these concepts. Before we get started and actually looking at the virtual 4-bar here, it'd be helpful to understand really quick how a 2-bar lift and how a 4-bar lift works and why a virtual 4-bar can help solve some of those problems. To help us with this, we're just going to imagine we have a simple arm system here with a gripper at the end of it. So I've just got a quick claw here. So if you use Lego Technic to describe this, you could think of this as the arm that's on top of the robot, and this is the actual arm that's rotating around. This would be a simple 2-bar lift. You have 1 bar that's attached to the robot and 1 bar that's actually rotating the object. Now imagine this green piece here is my claw. And if my claw stays in the same position as I rotate this arm, you'll notice that the green gripper arm changes its angle as that rotation moves through. Especially if we're trying to pick something up off the ground and place it at the same angle that we picked it up at, you can imagine a forklift, we actually want to be able to have this green arm rotate and stay parallel to the ground as we start. To solve that problem, engineers often turn to a standard 4-bar lift. So here, a 4-bar lift is essentially a parallelogram. You have 2 parallel bars here and 2 parallel bars here. And as I lift and rotate that one arm around these 2 joints, you'll notice that all 2 bars, each set of bars stays parallel to each other. You can also pivot it this way, where you'll notice that each set stays parallel to each other. So you've got your base, you have your 2 arms that pivot from that base, and then that 4th link is the coupler, and that connects the ends of these 2 arms together. And because it is a parallelogram, as that lift moves with that coupler link, where that gripper would be attached, it stays parallel to the base. So let's go ahead and add our simple claw arm here to the end of our gripper to that coupler, and you'll notice that as we lift ourselves up, that gripper stays parallel to the ground the whole time. Now, a 4-bar lift is fantastic for keeping things level, but a big downside of a 4-bar lift is that it can get really bulky really fast. You've got extra links taking up a lot of that physical space, and in Technic, it doesn't add a lot of weight, but if you were to use steel or aluminum or wood or acetyl or polycarb, you'd really start to add up a lot of extra weight, and it can potentially limit where you can even reach to. Another thing about having that second arm here is you'll notice that eventually the arms will hit into each other. So it does limit your reach in how far these arms are placed apart from each other at the start and the finish of that unit. So how do you get that same parallel motion as that standard 4-bar, but making it a lot more compact and most of the time lighter? And the answer lies in replacing one of those physical links, one of those arms, with a virtual one. And in this case, I've created a virtual arm here with a pulley and with a belt and some pulleys, but you could also do this with some sprockets and some chain. Both would be acceptable. So as I lift this up, you'll notice that the arm stays parallel. That end effector, our gripper, stays parallel with where our system is. So how does that actually work? So in our system, we have our main lift arm here. So I have 2 on this side, but you can effectively think of this like 1 arm. These are made of some acetyl plates. You could also make them out of aluminum, whatever it is you have. At the end of our arm, we've got our gripper on this pulley. And this is the gripper that has to be able to stay level as we lift up and down. So we need to ensure, in order for this gripper to stay level or parallel to the ground, we have to ensure that this whole end effector assembly counter-rotates relative to the main arm. So as this main arm rotates up, we need to make sure that this endpoint is counter-rotating against that other arm. Otherwise, we'd end up changing the angle of that gripper as we move up and down. Now, this is where that belt and pulley or chain and sprocket system comes in. You can see that on our system, we have two pulleys here. One pulley back at the main arm of the system, and a second pulley back here at the end effector. Now, the important thing about these pulleys is at the back of my arm here, this axle here is solid. It is directly tied in to the machine here. So as I rotate, you'll notice that this axle here does not pivot. And this pulley is directly constrained to this axle here. So as I rotate this arm, you'll notice that this pulley does not rotate. The gear on the outside and the arm itself rotates, but the pulley itself is not rotating. On the front end of our system here, we've got the other end of the pulley does rotate along with it. So let's give that a little rotation here. Notice that as I rotate up, that pulley is changing angles with that system. So I am free to rotate this pulley and this bar system. Key point here to notice about a standard virtual 4-bar is that the pulley here on this main arm is not directly on the pivoting axle of that main lift arm here. So if we look in close at this system, so if we're looking in at this system here, this gear and this acetal arm is on a ball bearing. So it's able to rotate around this axle, but it's not actually physically attached to this bearing here. So this whole arm rotates on these joints, and we can see that movement here. So this whole arm rotates here. And on the assembly side, where our gear is, this pulley here rotates independently of this arm. So this whole subassembly here is attached via a ball bearing to this lift arm here. So while the lift arm here is pivoting and the pulley is attached here, the pulley is free and the lift arm itself is free and the pulley itself is rotating. So it's actually the opposite. While the pulley is constrained, the pulley is unconstrained. While the arm is unconstrained, the arm itself is constrained. And that's how we end up getting that kind of virtual 4-bar with these pulley systems. Here's that main idea. As this main arm here rotates, the belt forces that gripper pulley to rotate. And if these pulleys are the same size, which these ones are, they're both a 1-to-1, the gripper is going to rotate by the same amount as that main arm does, but in the opposite direction relative to that arm itself. So that counter rotation, as this is rotating up this way, this is rotating the opposite direction, is what keeps that gripper level to the ground, or more accurately, keeps it parallel to its starting orientation. So as we can see that as that arm goes up, that gripper stays perfectly level to the ground the whole time. Let's show you a better angle here with something actually attached. So we can see that as we start with this cube in place, the cube stays at the same angle throughout the entire range of motion through this system. If you were to say take this back pulley and make it smaller than this front pulley, you would actually end up slowly changing the angle of your arm over time. And you may find that beneficial depending on what your robot's goals are. To think of it as another example, you can think of it as you've got one standard bar here in your 4-bar. This second bar here is that tension that used to be in the system with that 2 arms. This belt is now providing that second arm, but it's running over 2 pulleys. Why might you want to use a virtual 4-bar as opposed to a standard 4-bar? Well, it's a lot more compact. Using a standard 4-bar, we'd have to have an additional arm here, and that saves up a lot of space. It also allows us to rotate all the way around. So right now, I'm being constrained by my gripper hitting this bar, but if that bar were not there, I could actually rotate all the way around. And then I could have effectively 360 degrees of motion if nothing else were in the way. Belts and pulleys tend to be a little bit lighter than some of those solid metal links. And when you set this up, you get some really nice smooth motion that keeps things consistently parallel. And sometimes having this a lot more compact really helps things get a little more rigid. It also helps things be a little bit easier to put together as opposed to having to find places to put an additional 4-bar. So some challenges here. Belt tension is key. Some people use a pinch test, some people use a turn test. I like to use a turn test. You should be able to get to about 90 degrees without much tension, and it should be a little bit harder to get it to flip all the way over. In fact, you probably shouldn't be able to flip it all the way over. So this belt's probably a little bit loose. If it's too tight, you're going to increase that friction on your motor and it's going to be too hard. If it's too loose, you'll probably end up slipping a tooth. Another thing that's challenging about this is you have to be able to get your lengths proper for your belt length. Belts come in pretty standard lengths. And there are some calculators online. I'll leave a link down below so you can figure out what your proper length should be. But adding in a little tensioner or a little idler at the end of the day can always help with some of these problems if you do happen to not get it right from the start. So the virtual 4-bar is a really clever way to get that parallel lifting motion. It uses that pulley system. This pulley is constrained, this pulley is free, this arm is constrained, this arm is free to be able to create that 4-bar lift in a much more compact system. Being able to understand those different lifting mechanisms, the 2-bar, traditional 4-bar, and a virtual 4-bar gives you more options when you're designing your robot. Each of them has their own place. It's not like a 2-bar, 4-bar, virtual 4-bar are good or bad. They have their purposes. So the virtual 4-bar with a pulley driven or a sprocket and chain is a fantastic choice for lots of applications where you need to keep that end effector parallel to the ground. As well, it's also fantastic when you keep things nice and light. If you found value in this video and it helps you understand those virtual 4-bar lifts a little bit better, please hit that like button and consider subscribing for more robotics, programming, and design tutorials. It really does help the channel reach more people like you. Thanks for watching, and best of luck in your next robotics project.